Hello, everyone. I'm so excited to have you all here. Today, we are embarking on an extraordinary journey into deep space as we explore A Tale of Two Suns, the fascinating science of worlds that orbit two stars instead of one. To understand these worlds, we first need to look at binary star systems. Unlike our own solar system with its single sun, a binary system consists of two stars orbiting a common center of mass. Imagine two dancers spinning around a shared center. That's exactly how these stars move through the cosmos. When a planet revolves around both of these stars at once, we call it a circumbinary planet. It creates a unique environment that challenges everything we know about planetary stability. Many of you might be thinking of Tatooine from Star Wars. It's a classic piece of scientific curiosity. Could life actually survive and thrive under two suns? Throughout this session, we'll use physics and biology to find out if a real-life Tatooine is truly possible. Here is our roadmap for today. We'll start with gravity and orbital stability, move into the extreme climate conditions of these worlds, and eventually look at real-world examples discovered by our telescopes. Let's dive into the mechanics of how these systems stay together. To understand how these systems stay together, we need to look at the specific blueprints of their orbits. There are two main configurations we find in nature, the P-type and the S-type. First, let's look at the P-type, or circumbinary arrangement. If you've ever seen Star Wars, this is Tatooine. The planet orbits both stars from a distance, treating them almost like a single gravitational center. It's a wide, encompassing dance. Contrast that with the S-type, or satellite arrangement. In this case, the two stars are usually much further apart. The planet orbits just one star, staying close to its parent, while the second star remains a distant, very bright neighbor. Of course, these orbits aren't guaranteed to last forever. For a planet to be stable, it must stay within the Hill sphere, that's the invisible boundary where its host star's gravity is strong enough to resist the tug of the second star. If the planet wanders too far, we face orbital instability. The gravitational tug-of-war can become so violent that the planet is actually ejected, becoming a rogue planet drifting alone in the freezing dark of deep space. Next, let's jump into a simulation to see this gravity dance for ourselves. Welcome! Today we'll explore the complex gravitational dynamics of a planet orbiting two stars, known as a circumbinary system. This slider controls the distance between the two central stars. Closer stars often act like a single point of gravity. In this configuration, the stars are close together and equal in mass, allowing the planet to maintain a stable, circular orbit. The mass ratio determines if one star is significantly heavier than the other, shifting the center of gravity. Watch what happens when we pull the stars apart. The planet's path becomes chaotic as it is pulled between competing gravitational wells. Adjust the orbital radius to see if you can find a safe zone where the planet remains stable even in this difficult environment. Now that we've seen how chaotic those orbits can be from our simulation, let's talk about the direct consequence of those paths, the climate. When you have two stars, you aren't just dealing with complex gravity, you're dealing with a massive increase in energy output. First, let's look at the most immediate threat, extreme heat. In many binary configurations, a planet could receive double the solar radiation we experience here on Earth. Imagine the intensity of the sun at noon, but coming from two different directions simultaneously. This leads to what scientists call surface sterilizing heat. It's not just a hot summer day, it's an environment where the constant bombardment of radiation makes it nearly impossible for complex organic molecules to remain stable. In fact, research from Cosmoknowledge suggests temperatures could exceed 500 degrees Fahrenheit. That is hot enough to essentially fry most life forms instantly, turning a potentially habitable world into a barren kiln. However, the climate story isn't always about heat. There is also the very real possibility of extreme cold. Remember those unstable orbits we just looked at? If a planet is nudged into a much more distant orbit by the shifting gravitational pull of the two suns, the opposite happens. In these distant shifts, the planet faces severe global freezing. It's a delicate balance. Even a slight move further out could cause the atmosphere to collapse or freeze solid. This leaves us with a major question. Could any atmosphere even survive the combination of intense solar winds and these temperature swings? We'll keep that in mind as we move toward our gravity and heat check. Now that we've looked at the orbital physics, let's dive into the really exciting part, biology. If a planet successfully maintains a stable orbit, what would life actually look like under those dual skies? We're talking about a radical shift in how evolution might unfold. First, consider photosynthesis. On Earth, plants are mostly green because of the specific light our sun provides. On a binary Earth, plants might need to adapt to a much broader spectrum of light from two different stars. We might see plants with darker, even black pigments to absorb every bit of energy available from both sources. Vision would also be vastly different. While humans have 3 types of color receptors, binarian animals might evolve many more to distinguish between the overlapping light frequencies. Their perception of color would likely be far more complex than ours. One of the biggest challenges would be circadian rhythms. Our 2-4-hour day-night cycle is very consistent. But with 2 suns, you might have periods where one sun is rising while the other is setting, leading to almost eternal twilight or erratic light patterns. Biological clocks would have to be incredibly flexible. And finally, think about the visual reality of walking outside. You wouldn't have just one shadow, you'd have multiple intersecting shadows of different intensities. It would create a high contrast environment that would completely change how predators and prey use camouflage. Now that we've imagined the possibilities of life under dual skies, let's look at a concrete reality. This is Kepler 16b, a planet that made science fiction a scientific fact. Kepler 16b was the first confirmed circumbinary planet ever discovered. It orbits a pair of stars, one a K-type orange dwarf and the other an M-type red dwarf. If you stood on its surface, you would see 2 suns set every day, just like on Tatooine. However, looking at the technical data in this table, we see it's not exactly Earth-like. Unlike the rocky world we've been simulating, Kepler 16b is a cold gas giant roughly the size and mass of Saturn. It's composed mostly of hydrogen and helium, and it sits outside the habitable zone where liquid water could exist. Finding these worlds is an incredible feat. As we see here, the detection challenge is immense. Because the 2 stars are constantly moving around each other, their gravity creates a complex wobble. This makes it much harder to distinguish a planet's signal from the noise of the star's own orbital dance. This discovery was a breakthrough because it suggested that even with such chaotic gravitational interactions, planets can and do form in binary systems. It opens up half of our galaxy to the possibility of hosting planets. Next, we're going to use everything we've learned to design your own habitable binary world in our final project. Now that we've explored the real-world example of Kepler 16b on the previous page, it's time to put all our knowledge from today into practice. In this project, you will design a complete planetary profile for a habitable world orbiting 2 suns. You'll need to apply what we just covered regarding stable orbital distances, climate extremes, and the biological adaptations we discussed on page 6. I've set up roles for this mission. You can focus on the orbital calculations, the xenobiology of the inhabitants, or the engineering solutions for planetary defense against radiation. Choose the role that interests you most, and let's see if your world can survive the unique challenges of a binary system. Fantastic work on those projects, everyone. Seeing your designs for habitable binary worlds really highlights the complexity we've studied today. To wrap things up, let's reflect on why our own solar system is so unique. As we've seen, our single sun provides a rare kind of stability. Because we orbit just one star, Earth maintains a circular, predictable path. This Goldilocks arrangement has allowed for billions of years of climatic consistency, which is vital for the evolution of life as we know it. In contrast, we've explored the fascinating but hostile dynamics of binary systems. The chaotic gravitational dancing and extreme temperature swings we simulated earlier illustrate the immense hurdles life would face on a planet with 2 suns. The story doesn't end here, though. Next-generation telescopes are currently hunting for biosignatures in these complex systems. We are living in a golden age of discovery where the sci-fi worlds of our imagination are becoming scientific realities. If today's session sparked your curiosity, I've listed some excellent resources here, including the NASA Exoplanet Archive. Thank you all for your incredible participation. Before we finish, I'd love to hear your final thoughts on the future of this research.